Welcome to Target IES. I am Prakash Rajput and today we will discuss about electric potential. So to understand what is electric potential, let us consider here electric field lines are going through. They are generating from some charge distribution. So they are going like this. So now I have a one positive test charge here placed at location A and I want to move this test charge to location B. So here is my positive test charge placed at A and I want to move this charge from A to B along this path. Now you know that by Coulomb's law, if a charge is placed in electric field, it will experience some force that is given by Q times E. You know it that if a test charge is if a charge is placed in electric field, it will experience some force. So electric field lines are here all over and I want to move this charge from A to B. Now you also know that to move a charge, to move something from a location, we have to do some work. So suppose I am moving for a small length dl and that will be given as F dot dl, dot product of force and displacement. So to find the total work done, I have to integrate this for this path A to B. So it becomes A to B F dot dl. Now I am assuming here that the work is done against the field. For that I have to consider a negative sign here because I am considering the work is done against the field. So we can also say that the work is done by an external source so that's why we have to take here negative sign. So now I will write this here. So now I will write the F value, that is Q times E here. So work done will be integration from A to B minus Q E dot dl. Q E dot dl. Now here we define a term. Here we define a term called as electric potential, and this electric potential VAB. What is a VAB? I will tell you. VAB is the potential difference that is defined as work done per unit charge in moving a charge from point A to point B. So work done per unit charge will be defined as the potential difference or the electric potential, and you can write this VAB as this also, minus of integral E dot dl along the path, this dl vector from to move a charge from A to B. So here if you see that this is the electric potential, so it is defined as work per unit charge, so its unit we can write as joule because work done unit is joule and charge unit is coulomb, so joule per coulomb, or the famous unit is volts. So this is the formula to find the electric potential for moving a charge from A to B. Now we can write this formula like this: E dot dl A to B. If I write this minus sign here, so it can be written here E dot dl, and this can be written again like this from b to a minus E dot dl using integration property. Now what this can be? What this can be? If you see that we are moving from a to b, then it was minus E dot dl a to b. Here minus from b to a E dot dl. So you can say that this is the electric potential when we are moving the charge from b to a. So you can also say that minus of VAB is equals to VBA. Now if you see that, suppose this is my path A to B. Wait, this is my path. Suppose this is location A, this is location B. I am moving a charge from A to B, and that potential is VAB. And again, this potential, if I take the charge from B to A back, so this closes this path basically. So you can see here, what you can see, if you take this minus VAB on the right side here, this will become VAB plus VBA equals to 0. So what this means is, if you close the path, if this path gets closed, that is you move a charge from A to back to A, then the electric potential, or we can write it as the E dot dl from same position. So we can also write it as like a closed integral, like E dot dl, closed line integral of E dot dl will be 0. That is moving a charge from A back to A. That is closed loop line integral of E will become 0. This is Maxwell's second equation for static fields in integral form. Now if you remember, there was a theorem which is relating this closed line integral with the surface vector. If you remember, that theorem is Stokes curl theorem. Stokes curl theorem. So if I write, that says that the circulation, closed line circulation of a vector can be, their line integral can be written as curl of that vector with the surface that we are taking. So this will be the this was the Stokes curl theorem, because the loop will make a surface. Here also that you will see that this closed line is making this surface. So Stokes curl theorem says that the circulation of a vector over a closed loop will be equals to curl of vector over that surface formed by the closed loop. So you can apply this Stokes curl theorem here also. Here also we can apply this Stokes curl theorem. So you can write that E dot dl will be equal to what? It will be del cross E dot ds. And what is this value? If this path is closed, this will be 0. So you can also say that del cross E equals to 0. Del cross E equals to 0. This is Maxwell's second equation in differential form. In differential form. So this is Maxwell's second equation in differential form. Del cross E equals to 0. This is valid for, this equation is valid for uh, static electric fields, because here it is 0. But in case of varying magnetic field, you will see that later in the time varying field, here the field is static. That's why del cross E is 0. So this is Maxwell's second equation in differential form. Del cross E equals to 0. That is, we can also say that curl of electric field is 0. And I have told that when the curl of some field is 0, then that field is known as conservative or irrotational और irrotational। यानी कि हम इस इलेक्ट्रोस्टैटिक्स में स्टैटिक इलेक्ट्रिक फील्ड की बात कर रहे हैं, तो जो ये जो स्टैटिक इलेक्ट्रिक फील्ड्स हैं is conservative, so this is conservative and conservative or irrotational you can say, or irrotational, right? Irrotational. Now there is one more point for electric potential, that we are finding this E dot मतलब जो potential find out कर रहे हैं हम, V is equals to E dot dl minus integration of E dot dl. So here we have chosen this path. We can choose any path. Along any path you can take, the potential will come same. The potential will come same. So here you can say that the it is independent of the path chosen. This potential difference or electric potential you can say, potential difference between any two points, potential difference between any 2 points is independent of path chosen. किसी भी पाथ के अलोंग आप अगर इलेक्ट्रिक पोटेंशियल निकालते हो तो दैट विल बी सेम टू फाइंड आउट. So independent of the path chosen between the 2 points, between 2 points taken. So you can choose many multiple parallel paths and find that electric potential is same. Now let us see electric potential due to a point charge. So let us consider a positive charge placed at origin, and here is my test charge. I am moving this test charge from A to B. So this charge which is present at origin will have an electric field which is radially outwards. So what will be the electric potential due to this point charge? So you know that the electric field due to this point charge will be, suppose here I am considering a dl length. So electric field will be q, suppose this charge have magnitude q, divided by 4 pi epsilon naught, and the vector here, suppose let us say r vector. So q by 4 pi epsilon naught, r vector magnitude square, and direction will be ar cap. Let us say in this vector direction, this will be e. So what was VAB? It was minus of integral from a to b e dot dl. So here e is this. So what will be d? What will be dl vector? It will be, as the here the r is changing, so you can write it is dr. So here minus a to b, and the value of this is q by 4 pi epsilon naught 1 by r square, here ar cap, and dl is also dr ar cap. Ar cap dot ar cap will become 1. Here it will be right minus a to b, and q by 4 pi epsilon naught 1 by r square dr, 1 by r square dr. Now simply integrating this, what it comes? So q by 4 pi epsilon naught I can take out of integration. Here integration of 1 by r square will come as minus 1 by r, and here minus sign was already there. from A to B. If I put the limits, it comes as minus q by this minus and this minus gets cancelled, so I can write as q by 4 pi epsilon naught 1 by r b minus 1 by r a. This will be the value of VAB, moving a charge from A to B in presence of electric field due to point charge. So this will be the value of q by 4 pi epsilon naught 1 by RB minus 1 by RA. Now this can be also written as q by 4 pi epsilon naught 1 by RB minus q by 4 pi epsilon naught 1 by RA. This can be also written like this. Here this q by 4 pi epsilon naught 1 by RB can be said that this is VB, and this can be said that this is VA. What is VB? VB is absolute potential at B, and this is absolute potential at A. So what are these absolute potential? So absolute potential is the potential difference between the point which I am considering. Suppose this is absolute potential at B. So it is the potential difference between B and a reference point that is present at infinity. A reference point that is present at infinity. So this is the potential at point B with reference to potential at infinity, and this is the potential at A reference reference with potential at infinity. So these are called as reference absolute potential. So I can write VAB as VB minus VA, VAB minus VA. Or if we are moving a charge from B to A, so as I have told earlier that VAB is nothing but VBA is nothing but minus of VAB, so it will be VA minus VB simply, right? Now if you think that we are moving a charge from infinity to a point, we are moving a charge from infinity to a point, moving a charge from infinity to a finite distance point, say at location r with, with reference to origin, from infinity to a point whose distance is r from origin. So V will become at that point, here I have derived VAB when I was moving the point from A to B. So I am moving now from infinity to point where distance is r, where distance is r. So here this RA becomes what? Infinity. So 1 by infinity becomes 0. Only this remains. So q by 4 by epsilon naught r will be the value of electric potential when we are moving a charge from infinity. So it will be q by 4 pi epsilon naught r, q by 4 pi epsilon naught r, if we have a reference point at infinity, if we have a reference point at infinity. If we have a reference point somewhere in the finite range, then this formula becomes q by 4 pi epsilon naught r plus c, where will be calculated c will be calculated, or it will be given in question sometime, that what is the potential with the reference point. So you can simply calculate this. We will see that in this while we solve question. You just remember, if the reference point is infinity, if reference point is infinity or is at infinity, this formula will be applicable. If reference point is other than infinity, if reference point is other than infinity, then we have to use this, because here this term will come, the constant will come, because our reference point has changed from infinity. Okay, now we have seen that the point charge is present at origin, then electric potential is this or this depending on the reference point. Now if the point charge is present other than infinity, other than origin somewhere, like if I show the point charge is suppose present here, and the vector to this position vector is suppose r vector, and I want to move a charge from infinity to this location, and this has a position vector r1 vector, right? So here is my charge placed. So due to this, the potential will be given as what we have calculated earlier for the potential due to point charge. It was 4 q by 4 pi epsilon naught r if the reference point is at infinity. So r is basically what? R is distance from origin to the point we are taking, right? Like this. So r is the distance from the origin at which we are calculating the potential. So here the value will be, value of potential at this point will be q by 4 pi epsilon naught, and the distance from the charge what it will be. So distance from this point to this point, what it will be, location of this point, that position vector of this point minus this point, and its magnitude we can take. So it will be r1 vector minus r, or wait, not r1 vector, this is actually charge is placed at r, so the displacement will be from here to here. So we are taking for the, my point is present here, the charge is present here, for which I am calculating, for which I am moving from infinity to this point. So I am calculating absolute potential at this point. So it will be q by 4 pi epsilon naught, and the distance between this point. So it will be magnitude of r1 vector minus r vector. This will be the value of absolute potential, I can say, because I am calculating with respect to infinity. So this will be the formula, and this will be the formula again if the reference point is infinity, reference at infinity. अगर रेफरेंस एट इन्फिनिटी नहीं है तो फिर से इसमें क्या हो जाएगा, एक कांस्टेंट c इंक्लूड हो जाएगा, q बाय 4 पाई एप्सिलॉन नॉट r1 वेक्टर माइनस r वेक्टर मैग्नीट्यूड प्लस c if reference is other than infinity, if reference is other than infinity, other than infinity. Okay, let us see some important comments about work done. So work done is what? It is minus q integral of E dot dl. So first point is, if the work is done, or if the work done is positive, if the work done is positive, this means that if the work done is positive, it means work is done by external source, yeah, external agent. Work is done by external source or external agent, because in this case work is done against the field. Work is done against the field. Now if you see that work done comes negative, if work done is negative, work done is negative, so what it will mean? If work done is negative, it means work is done by by electric field which in which the charge is present. Work is done by electric field, that is charge will be moving along the direction of electric field, which means that it is moving because of the electric field force, and in that case work is done by the electric field and it comes out to be negative. So here the work is along the field, work is along the field, or work is done by the field, you can say. In fact, work is done by the field, I have already written that it means that work is done by the electric field. Now the third point is that you are finding potential from A to B point. It does not depend on the path. Suppose I am moving a charge from A to B like this. Suppose this is my point A, this is my point B, as I've told earlier. At every point I have to take what? E dot product with dl. So what will happen is, at this point the dl vector will be this. Suppose this is dl1. At this point it will be something like this dl2. At this point it will be something like this dl3, right? So what happen is, if you know about the addition of vector form, that is polygon law, if you make these vector in a polygon form, dl vector, dl2 vector, dl3 vector, dl4 vector, and goes to B point and take uh, some other path also, like this, like this. So they are also dl vector only. If you add up all these, dl1 plus dl2 plus dl3, it will both the path here, this path or this path, or you can take any other path also, all will give the same answer, that is nothing but AB vectors magnitude, AB vector magnitude. Because what the polygon law says is that joining all these vector will result, their resultant will come equal to the joining a vector, joining a vector with initial point and the final point. This will be the final result only. So as the final result is, suppose this is LBA, the position, the displacement vector LBA. If I write here as LBA, this will be, and ultimately I have to do what? Dot product of E dot LBA. So here you can see that if you join any of these vector additions of the along the first part or the second part or any other path, it will result in this vector only LBA, and I have to then dot product with E. So the result I will get for every path will be same. So that's why the work done, that is minus Q integral A to B E dot dl, ultimately the result is E dot this part, this thing, E dot lba, it will be same. So for every path I will get same answer. So work done is independent of path. Work done calculated is independent of the path chosen. Independent of the path chosen. Independent of the path chosen only depends on initial and फाइनल पोजीशन. तो सिर्फ और सिर्फ इनिशियल एंड फाइनल पोजीशन पर ही डिपेंड करेगा कि आप कैसे वर्क डन कैलकुलेट कर रहे हो. ठीक है. अब जैसे वर्क डन कैलकुलेट कर रहे हो वैसे वर्क डन पर यूनिट चार्ज यानी कि ई डॉट डी एल भी क्या हो जाएगा, इंडिपेंडेंट ऑफ द पाथ चूजन, दैट इज पोटेंशियल डिफरेंस आप निकालना चाहते हो वो भी क्या होगा, independent of the path chosen, and it will also depend only on the initial and the final position. Understand? Now see here one question. A point charge q equals to 0.4 nanocoulomb is located at origin and obtain the potential difference at of point A. Potential difference of point A or at point A you can say. So due to a point charge, what is the potential at A? I have to find absolute potential. So I am moving a charge from infinity to point A basically. You can understand this. So q by 4 pi epsilon naught, and as the charge is present at origin, so it will be q by 4 pi epsilon naught Ra, just that, because I am moving a charge from infinity here. So there will be no C. Okay. Now what will be Ra? If you see that here origin and here is my point A. So Ra will be this position vector magnitude. So Ra can be calculated as by distance formula. It will be like 2 minus 0. 2 here, this point is 2, 2, 3, and here this is origin 0, 0, 0. So it will be 2 minus 0 ka whole square, 2 minus 0 ka whole square, 2, 3 minus 0 ka whole square, and add all these. So it will be 2 square plus 2 square plus 3 square. And if you solve this, it will come as 4 plus 4 is 8, 8 plus 9 is 17. So you can write this here. 1 by 4 pi epsilon naught value is 9 into 10 to the power 9 into 0.4 into 10 to the power minus 9 divided by under root of 17. And this 10 to the power 9, 10 to the power minus 9 gets cancelled. 9 into zero point 0.4 is 3.6 by root 17 volts. This will be the absolute potential at A. Absolute potential means that with reference to infinity due to the point charge of zero point 0.4 nanocoulomb. Now if the same charge q minus q is equals to 0.4 nanocoulomb is located at 233, instead of origin it is located at 233 point, then find the absolute potential at the location 223. So for that the formula was q by 4 pi epsilon naught magnitude of the distance between them, that is Ra minus R. Ra minus R. Previously I have written R minus R1 because I have considered R vector here and R1 vector for the position vector of charge. So if you think of the coordinate system, here will be my point, my charge is present, which is at 2, 3, 3 location, and somewhere here, or you can understand it is little below that, here 2 to 3 distance पर ये मेरा charge located होगा. I mean I'm finding this is my point A. At this point I am finding the potential. So this I have to find the distance between these 2 points basically, that is Ra minus R magnitude. So what it will be, simply points coordinates of A, my मतलब distance formula से 2 minus 2 का whole square plus 2 minus 3 का whole square plus 3 minus 3 का whole square. If you solve this, what will come? Under root of 1, that is 1. So you can directly write 0.4 into 9. It will come as 3.6 volt when the charge is present at this location instead of origin. Then the absolute potential at A point is this. Now you understand when the charge is not at origin, then how to use the formula. Now see here one question. A point charge of 6 nanocoulomb at origin in free space is located at origin in free space. Find the potential of point P. Find the potential of point P. This is the potential. This is the point at which we have to find the potential. And a part is when V is equal to 0 at infinity. What this means is, in the formula we have written V is equals to Q by 4 pi epsilon naught R when the charge is placed at infinity. And this is the formula when our reference point is infinity. What it means is reference is infinity. At infinity, the potential is 0. We have assumed in this formula Q by 4 pi epsilon naught R that reference is infinity, and by this we mean that at infinity the potential is 0. Okay, but now you see the B part. B part says that V is equals to 0 at 100. Now this is the reference point basically. Okay, this is the reference point at which V is equal to 0. Yet at infinity V is not 0. At infinity V is not 0. It is 0 at this location. So we have to find potential with this reference. So let us first do the first part, then we will move on that how to deal with it. So in the first part it is a simple one that I have to find for this V at infinity, V equal to 0 at infinity. Now I have to find Vp. So it is the same formula Q by 4 pi epsilon naught R, and the Q is here 6 nanocoulomb. 1 by 4 pi epsilon naught value is 9. So here 6 into 10 to the power minus 9, and here 9 into 10 to the power 9, 10 to the power minus 9 and 10 to the power 9, but will get cancelled. So only thing remaining is R. So what will be the R? R can be simply calculated the distance from the origin to this point. So it will be 0.2 minus 0 square plus minus 0.4 minus 0 square plus 0.4 minus 0 square. So you can simply solve this. So if you solve this, it comes out to be 0.6. So Vp will come as 6 into 9 by 0.6, and if you solve this it will be 90 volts for when the reference is at infinity. So reference at infinity means that at infinity the potential is 0. Now if I do the B part, what the B part says is that our V is equal to 0 at 100. V is equals to 0 at this location. So for this what I have to do is, suppose I'm writing this B part. So V is equals to 0, and we know that when the reference point is shifted, the what is the formula? Q by 4 pi epsilon naught R plus C. Now at the point this, for this V is 0. V is 0 and Q value is 6 into 10 to the power minus 9, and 1 by 4 pi epsilon naught value is 9 into 10 to the power 9 divided by R. The distance for this point will be, if I calculate, it will be under root of 1 square plus 0 square plus 0 square. So it will be simply what? 1 only. So I can write 1 and plus C. So if you solve this, what will be the C value? C value will come as minus 54. 6 into 9, 54. This will come on the left hand side. So the value of C is minus 54 for the B part. So now I can use the formula for Vp. to find the potential at point P. Q by 4 pi epsilon naught R plus C. Now we have calculated this value 6 into 9 upon R. R value I can take from here. Suppose this is RP only. Okay, because this is here I have written R and here also R. So this value will be 0.6 and here I will place the C value as minus 54. So here 90 minus 54 will result in 36. So potential at point P, now it will be 36 volt. Now it will be 36 volt for the B part. For the B part, because I have shifted my reference to point 100. Now if the reference is shifted again, and reference is shifted to V equals to 20 at this point, minus 0.5, 1, minus 1. So for this, what I have to do, I have to find again the value of C. I have to find the value of C again. So let us do the C part. So here C part, V is equals to 20 at point minus 0.5, 1, and what was the other value? Minus 0.5, 1 and minus 1. 1 and minus 1. So for this I can apply the formula 20 equals, that formula V is equals to Q by 4 pi epsilon naught R plus C. So here V is 20, Q value is 6 into 10 power 9 minus 9, and 1 by 4 pi epsilon naught is 9 into 10 power 9 divided by R. R can be calculated as from the distance formula. For this point, here R will be 0.5 square plus 1 square plus again minus 1 minus 0 is again 1 square. So if you solve this, under root of 0.5 square plus 1 square plus 1 square, so this will come as 1.5. This will come as 1.5. Okay, so I can write the value here 1.5 and plus C. So I can solve this value, 54 divided by 1.5, and this will be 20 equals to, this will be solved as 20, 6 into 9, 54. 54 divided by 1.5 is 36 plus C. So value of C comes out to be 20 minus 36. So it will be minus 16. Now I have to use C value as minus 16 in the formula for the point P. It will be again Q by 4 pi epsilon naught R plus C. So here the value of Q is same, 6 into 10 power minus 9, and 1 by 4 pi epsilon naught value is 9 into 10 power 9. R value remains same for the point P. It is basically RP I have written. So here it was 0.6. We have solved this earlier, 0.6. You see here. Okay. So I have put this and the value of C. C is minus 16. So we have solved this as 90, and 90 minus 16 is 74. So if the reference point is shifted, our potential also gets changed because reference is changed. So with reference to the with reference to this point at which potential is 20, the potential at point P is 74 volts. Now you have understood, I guess, that if what it means by the reference is changed and what is the use of this, that C in the formula. Understood? So that's all for this video. We'll meet in the next lecture and see few more things. Thank you.